Most of the important and interesting things that go on in electronic devices and circuits are concerned with the dynamics, the sequence of cause and effect. What do charge carriers do in response to applied excitations? The use of visual animations opens up an additional dimension, the time axis, in teaching physical principles. This tape is the first result of a computer animation project for instructional purposes. The subject is active devices, transistors. All active devices which give gain work on the same basic principle, charge control. The essential feature is that the output current is a rate of flow of charge, and the amount of charge in transit through the active region of the device is determined by the amount of charge placed on the control electrode. Whether the device is a MOSFET, a JFET, a BJT, or even a TUBE, they all are three-terminal or two-port devices and work on the charge control principle. The rate of charge collection at the output port is controlled by the amount of charge placed on the input port. I'm going to illustrate this for two devices, the MOSFET and the BJT. But first, I want to introduce the representation of controlled and controlling charge in terms of a reduced version of an active device, a two-terminal or one-port device, the resistor. This represents a resistor with two terminals or electrodes which connected to an external circuit. The blue particles with plus signs represent fixed positive lattice ions, and the red particles with minus signs represent mobile negative electrons. In thermal equilibrium, the resistor is charge neutral, and the number of negative charges equals the number of positive charges. When the external circuit is closed, an electric field is applied between the two electrodes, which exerts a force on both sets of particles. The positive charges are fixed and can't move, but the negative charges can move and so carry current. There is now a steady state or DC current flowing around the closed circuit. There are two important features illustrated by this model. First, the total number of negative charges remains the same as before, equal to the number of positive charges. This is identified as the total charge in transit through the active region of the device. Even though the total charge remains the same, negative charges appear at the bottom electrode at the same rate as they disappear from the top electrode, and it takes a typical electron a certain length of time to make the journey through the active region. I'll follow one electron from the bottom. There's its having its transit time from the bottom electrode to the top electrode. This is the mean transit time of electrons through the active region. The resulting current is equal to the total charge in transit divided by the mean transit time. This is the basic relationship of charge control, sort of an integrated form of dq by dt. The second important feature of this model is that the top electrode controls the amount of current and collects the current. That is, there are two distinct functions, control and collection of current. And in the resistor, one electrode performs both functions. To make an active three-terminal or two-port device, one merely has to separate the two functions, so that the current at the output electrode is controlled by a different electrode, the input terminal. This represents an FET. The active region is the channel, with two electrodes, the source at the bottom and the drain at the top. An electric field can be applied along the channel by closing an external circuit. But now, unlike in the resistor, no current results because there are no available mobile electrons. What's needed is to make mobile electrons available in the channel. This is done by the gate, which is a third electrode separated from the channel by an insulating layer. When positive charge is placed on the gate, an equal negative charge is induced in the channel. This is just like charging up a capacitor. In fact, the gate and channel, separated by an insulator, constitute a rather distorted parallel plate capacitor. There are now mobile electrons available in the channel so that, when the drain circuit is closed, current flows in the output circuit. The basic charge control relation applies. The output current is the total charge in transit divided by the mean transit time. However, the charge in transit is equal, in magnitude, to the amount of charge that was placed on the gate. Thus, the output current is controlled by the charge placed on the input electrode, and the property of a two-port active device is achieved. The FET acts as a controlled switch. When there was no positive charge on the gate, there were no available mobile electrons in the channel, and the source and drain terminals behaved as an open switch. When there is positive charge on the gate, there's an equal number of negative electrons in the channel, and the source and drain terminals behave as a closed switch. If the FET switch is to be turned off, the available negative electrons must be eliminated by withdrawing the positive charge from the gate terminal. Let's repeat the off-on-off sequence with the output circuit closed to begin with. Initially, no current flows. The FET switch is off. It's turned on by placing positive charge on the gate. Note that gate current flows while the gate is being charged, but stops once the charging is complete. However, the drain current continues after the gate current has stopped. The FET switch can be turned off again by withdrawing the positive charge from the gate. Note that transient gate current flows in the reverse direction while the gate capacitance is being discharged, but stops once the discharge is complete. Here's another repeat of the off-on-off sequence with a larger amount of gate control charge. The transient charging gate current is increased, and so is the number of electrons available to carry output current. The transient discharging gate current is also increased. It's obvious that there's a speed concern to do with closing and opening the switch. The drain current does not start and stop instantaneously. If you want the switch to close faster, you have to stuff the gate charge in faster, requiring a larger transient gate drive current. If you want the switch to open faster, you have to yank out the gate charge faster, requiring a larger transient gate reverse current. Thus, for fast operation of the switch, the gate drive must be able to both source and sink sufficient current. Here's the simplest possible equivalent circuit model to represent the terminal properties of an FET. The drain current is a control generator labeled as the total charge in transit, Q minus, divided by the transit time, tau t, where the total charge in transit, Q minus, is equal and opposite to the total gate charge, Q plus. The controlling charge, Q plus, is supplied or withdrawn by the gate capacitance transient current, dQ plus by dt. The output control generator and the input capacitance are the two essential elements required in an equivalent circuit model. Below are simplified graphs of the gate and drain currents as functions of time. To turn the device on, the required gate charge must be supplied by the transient gate current. During the time the charge is being supplied, the drain current is rising to its final value determined by the amount of charge that has been supplied. The FET is now on as a switch. To turn it off, that same amount of gate charge must be withdrawn by the reverse transient gate current, causing the drain current to decay back to its zero value corresponding to the off condition of the switch. To turn the device on as fast as possible, the given gate charge has to be supplied as rapidly as possible, requiring a larger value of the transient gate current. Likewise, to turn the device off faster, that same amount of charge must be withdrawn faster, requiring a larger negative reverse gate current. The minimum attainable values of the rise time and the fall time are on the order of the mean transit time of the electrons through the active region of the device, namely the channel. The FET, the field effect transistor, is a basic charge control device in that the drain or output current is controlled by the gate or input charge. The BJT, the bipolar junction transistor, is also a charge control device, and its basic operation is exactly the same. This represents an NPN BJT. The active region is the base region with two electrodes, the emitter junction at the bottom and the collector junction at the top. Initially, there are essentially no electrons in the base region. They are minority carriers, and so no collector current flows even if the output circuit is closed. The emitter and collector terminals behave as an open switch. To close this switch, electrons must be made available in the base region. This is done by the base terminal. When positive charge is placed in the base region in the form of majority carrier holes, an equal negative charge of electrons is injected into the base region from the emitter junction. These electrons are available to carry current through the base region and constitute the steady state or DC collector output current. To open the BJT as a switch, the positive hole charge must be withdrawn from the base terminal, eliminating further electron injection from the emitter, turning off the collector current. The basic operation of the BJT is exactly like the FET. Output current is controlled by input charge. Input current only flows when the controlling charge is being changed. Externally, the base emitter terminals behave as a capacitance, known as the storage or diffusion capacitance. Positive base current charges up the diffusion capacitance, turning the collector switch on. Negative base current discharges the diffusion capacitance, turning the collector switch off. The more positive charge is placed into the base terminal, the more negative electrons are injected from the emitter and are available to carry collector output current. The faster you want the switch to turn on, the faster you have to stuff positive charge into the base, requiring increased turn-on base current. The faster you want the switch to turn off, the faster you have to yank the positive charge out of the base, requiring increased turn-off base current. There is, however, one significant difference between the BJT and the FET. In the FET, the positive controlling charge and the negative controlled charge are separated by the insulating layer that constitutes the dielectric of the gate capacitance. In the BJT, the positive controlling charge of holes and the negative controlled electron charge occupy the same physical volume, the active base region, which constitutes the base diffusion capacitance. Since the holes and electrons both exceed their thermal equilibrium densities, there is a net recombination of electron-hole pairs. This is illustrated here by a little explosion, as an electron and a hole disappear by recombination. If the same steady-state DC collector current is to be maintained, lost holes must be replaced through the base terminal at the same rate as they are lost by recombination. You can see this happening for each lost hole. I'll use the pointer to follow one particular recombination event. The result is that there is a steady-state DC base current required to maintain a given total charge of holes in the base region in the presence of recombination. From a device point of view, the steady-state base current is a second-order effect and is undesired. Great effort is made by device designers to minimize recombination in order to keep the DC base current as small as possible, indicated by a pink color in this animation. The same simple equivalent circuit model applies to the BJT as to the FET. In fact, this is the same drawing. The collector current is a control generator labeled as the total charge in transit Q minus divided by the transit time tau t, where the total charge in transit Q minus is equal and opposite to the total base charge Q plus. The controlling base charge Q plus is supplied or withdrawn by the diffusion capacitance transient current dQ plus by dt. The same simplified graphs below represent the base and collector currents as functions of time. However, in the BJT, recombination must be accommodated in the model. This is done by addition of a resistance which accounts for the steady state or DC base current. The corresponding non-zero maintenance base current appears in the graph below. The value of this current is the total positive charge of holes, Q plus, divided by the mean lifetime, tau, of hole electron pairs in the active base region. The ratio of the DC collector current to the DC base current is seen to be tau over tau t, usually referred to as beta or HFE. The important point about the second-order recombination process is that it contributes only a small DC component of base current and has no effect on the relatively large transient base currents required to turn the collector current on or off. These animations illustrate only the basic principle of active devices. They are all charge controlled. The voltage or current needed at the input to provide a given amount of controlled charge is, from a device point of view, a secondary consideration. The presence of an input capacitance is inherent in the device. To make the device operate fast, the controlling charge must be supplied or withdrawn fast, requiring a large transient drive current. This is the same for the FET and for the BJT. In the BJT, the controlling charge must be maintained in the presence of recombination by a relatively small DC current. Since the only significant difference between an FET and a BJT is the presence of a maintenance input current in the BJT, it seems anachronistic that a completely different set of names is used for the three terminals of the device. Since the TUBE is also a charge-controlled three-terminal device, there are three different sets of names to contend with. Let's see if we can choose a single set of names that would be appropriate for all charge-controlled devices. Drain is an unattractive name for the output terminal, suggesting that the charge in transit is discarded, whereas actually it's the important quantity to be preserved. I vote for collector as the surviving name, having a more positive connotation. Since emitter is already paired with collector, I vote for emitter as the surviving name, especially as it acknowledges a faint connection to the TUBE, whose cathode was originally merely a filament that emitted electrons. Also, since source would no longer be used, there could be no confusion with signal source. Base is a name that really needs to be banished. The original transistor was the point contact transistor, of which the largest physical component was a semiconductor base upon which two tiny metal points were pressed. Similarly, in the alloy junction transistor, the semiconductor base remained the largest physical component. However, in the grown junction transistor and its numerous descendants fabricated in integrated circuits, the physical proportions are completely reversed. The base, the active region of the device, is made as small as possible compared to the emitter and collector, which makes it the most difficult of the three terminals to connect to electrically. Grid is an obsolete name, and so, in my opinion, there's no contest, and the surviving name should be gate, especially as it has the connotation of control. Although this universal terminology is not likely to be widely adopted, it has the advantage that a single set of symbols and subscripts applies to all charge-controlled devices. The superscript plus is dropped, since there is no longer any need to distinguish the charge in transit from the control charge. The universal model relates various currents to the control charge Q, but for circuit analysis purposes we want to relate the currents to terminal voltages. These relationships are nonlinear. After offsets are accounted for, the collector current IC is related to the gate emitter voltage VGE approximately by a 3/2 power law in the TUBE, a square law in the FET, and an exponential law in the BJT. In this respect, the TUBE is the least nonlinear and the BJT is the most nonlinear of the three devices. The standard approach to doing analog circuit analysis is to make a small signal linearized model of a nonlinear device, whose elements are the slopes of the large signal characteristics evaluated at the operating point. A small signal universal device model is labeled with lowercase symbols and subscripts, and the two basic elements are the transconductance GM and the gate emitter capacitance CGE. In the BJT, a third element represents the non-infinite beta. I'll call this Model 1 for convenience in reference. The position interchange between the capacitance and the resistance is immaterial. This model and its following descendants is valid up to frequencies whose period is longer than the transit time tau t. Qualitatively speaking, if you've stuffed in a charge Q but yank it out in less than the transit time, the collector doesn't know what happened. The sole purpose in life of an equivalent circuit model is to give you the right answer. The small signal universal device model can be manipulated into many equivalent versions, choice of which is determined by advantages in obtaining certain answers. There is a choice of whether to include the capacitance within the manipulations or to leave it untouched outside the manipulations. Here's one such equivalent circuit with the capacitance left untouched or external. Model 2 incorporates the requirement that the emitter current is the sum of the collector and gate currents, and defines an emitter resistance, Rm, equals alpha over Gm, where alpha is beta over 1 plus beta. In this model, the input voltage VGE is the excitation, and other voltages and currents are expressed in terms of VGE. This version is appropriate when the device is embedded in a circuit upon which loop or node analysis is to be conducted. However, for low entropy design-oriented analysis, the same model with current excitation is often more convenient. Here's Model 3 with the emitter current as excitation, and Model 4 has the gate current as excitation. Models 2, 3, and 4 illustrate versions of the T model, which display the property that the currents in the three legs of the T have fixed ratios. The T model is especially useful when the external circuit contains elements in series with one or more of the three legs of the device model. The manipulations of the T model can be repeated with the capacitance CGE included, or internal, as in models 5, 6, and 7. The currents in the three legs of the T still have fixed ratios, but their ratios are frequency dependent and are conveniently expressed in terms of the alpha and beta cutoff frequencies. For frequencies below the beta cutoff frequency, these models, of course, revert to models 2, 3, and 4. An advantage of the T model with the capacitance included is that impedances can be reflected from the gate lag to the emitter lag or vice versa. This technique, with the capacitance omitted, is developed in Chapter 2. If the capacitance is included, insight can be gained into the cause of potential instability of the emitter-follower circuit. Within the frequency range between the beta and alpha cutoff frequencies, the emitter-gate current ratio is proportional to complex frequency S, causing a source resistance to be reflected to the emitter lag as an inductance, and a load capacitance to be reflected to the gate lag as a negative resistance. The emphasis here is on the commonality of the basic functions and the equivalent circuit models of all charge control devices, and only basic effects have been included. However, as already mentioned, the nonlinearities can be considerably different, which leads to significantly different dependencies of the small signal equivalent circuit elements upon operating point. In particular, in a BJT, the relation between the collector current and the gate voltage is exponential, with the consequence that the transconductance Gm, which is the slope of this large signal characteristic, is a function only of the large signal operating emitter current IE and the thermal voltage Kt over E. Thus, Gm and hence Rm are determined solely by the device operating current and are independent of its physical structure or materials. In contrast, in the FET, or TUBE, the Gm contains the proportionality constant between the collector current and the power law of the gate voltage, and so Gm and hence Rm are determined not only by the operating point, but also by the device internal structure and materials. So you have to look to the device datasheet to find the value of Gm or Rm. Any of the equivalent circuit versions of the basic charge control device can be augmented by numerous parasitic elements that also may have different operating point dependencies in the different devices. The most important of these are usually non-zero admittances from the collector to the gate and to the emitter, which led the augmented equivalent circuit to be known as the pi model. Addition of CGC, represented by the base collector capacitance CT of a BJT, is treated by use of the extra element theorem in Chapter 6. I've been taken to task by some because this entire course employs BJTs represented by Model 4. Why aren't there any examples employing FETs? The answer is, there don't need to be any. Model 3 or Model 4 represents a BJT or an FET. The FET is a simpler special case with beta gone to infinity and alpha gone to 1. It's easy to throw a parameter out of the answer, but you can't put it back in without going through the solution again. To make this perfectly clear, I've repeated Model 4 without the capacitance, labeled with the conventional BJT terminal terminology as used in the course, and shown the corresponding simplified Model 3 with the conventional FET terminal terminology. Therefore, all the methods and all the examples in the entire course apply equally well if the devices are FETs.